Okay, so this is lesson 3.5 on exponential and logarithmic models. Models means word problems. And we have 5 different types of models that we're talking about in this section, although I only have examples right now of exponential growth and exponential decay. But all 5 of these models and their general forms are on the screen currently. We're also going to deal with Gaussian, which for those of you that have taken AP stats, you might recognize that as the equation of the normal distribution. Logistic growth, which occurs when we have limits on the population. And logarithmic models, which obviously involve logs. So our first example, we have a population that can be modeled by this exponential function, y equals 1.8 e to the 0.026x, where x equals 0 corresponds to 1990. And what year did the population of this city reach 2.5 million? So we are trying to find x, which is a year, and we are given this equation, and we want to find in what year does the population equal 2.5 million. So we have 2.5 equals 1.8 e to the 0.026x. All right, so our first step has to be to divide both sides by 1.8. And that's going to give us 2.5 over 1.8 equals e to the 0.026k. All right, now we need to get rid of the e, so we're going to take the natural log of both sides. ln of 2.5 over 1.8 equals ln of e to the 0.026x. All right, now the ln and the e are gone. Bye-bye. We now have, I'm going to reverse the sides, 0.026x equals the natural log of 2.5 over 1.8. All right, so in order to find x, we're going to divide both sides by 0.026. X equals natural log of 2.5 over 1.8, all divided by 0.026. Now, at any point, I could have put this in the calculator. I chose not to. I'm going to put it in the calculator now as my very last step. So, in the calculator, natural log of 2.5, close, nope, not close, sorry, divided by 1.8, now close, all divided by 0.026, enter, 12.6. But what does that mean? That does not mean, or 12.6 what? There we go. All right. Well, x equals 0 corresponded to 1990. 12.6 would be the number of years after 1990. So 12.6 is going to be during the year 2002. So that is when population will reach 2.5 million. All right, our next example. 2 hours after a bacteria were introduced, we were given a population of 256. 5 hours after that, the population is 541. What's the population 24 hours? So it's important to note that we do not know the population at time 0. We only know the population when t equals 2. Population is 256. And when t equals 5, nope, when t equals 7. Be careful. P equals 541. We want to know when t equals 24, what p equals. Okay? And bacteria do grow exponentially. Okay? We're assuming exponential growth here. Now the model for exponential growth is going to be P equals the model for exponential growth is going to be y equals a e to the b t. Some books use k, ours uses b. Doesn't really matter. Where we know that b is greater than 0. That's because it's growing. Okay? So, we don't know what a is. We do know that when we have a e to the 2b, that we have 256. And we know that when we have a e to the 7b, that we have 541. So, what we're going to do is we're going to solve one of these. So, we're going to solve one of these for A and substitute it into the other. That'll help us find A, and it'll help us find B, which we need to know in order to make the model. So, I'm going to solve the first one for A. 256 equals a e to the 2b. Divide both sides by e to the 2b. And you could write this as a equals 256 e to the negative 2b because of exponent rules. Now we're going to replace that in the other equation. So that is 541 equals 256 e to the negative 2b e to the 7b. Now, anytime we multiply together two things with the same base and different exponents, we can add the exponents. So that's going to be 541 equals 256 e to the 5b. And now, divide both sides by 256. So e to the 5b equals 541 over 256. Natural log of both sides gives us 5b equals the natural log of 541 over 256. And then finally, b is 1/5 the natural log of 541 over 256. Now, it would be a really good idea to store this in your calculator at this point. So I am going to store this in my calculator as b. One divided by 5, ln 541 divided by 256, close, store, alpha b. All right, so now it's stored, and I have a decimal approximation, so that's cool. I need to know what a is as well. All right, so a is 256 e to the negative 2b, and I just stored my value for b. So that's going to be 256 e, oh, not ln, e to the negative 2 alpha b. And we get that that's 189.78 approximately, which is going to be about 190. We're going to store that as well. Store alpha A. All right. Now we have all the information we need to find our value. We are looking for the population at time 24 hours. So our model is population equals A e to the b t. We know what A is. We just stored it. We know what B is. We just stored it. We know that T is 24. So in my calculator, I put alpha A e to the 24 alpha b. Oh, that's the wrong thing. Alpha b. All right, and so now we hit enter, and we get 6,887.3. Now, we cannot possibly have a fraction of a bacterium, so in reality we're going to say that we have 688 or 6,887 bacteria in the population. More to come in the next video.